In today's data-driven world, innovation and data integrity are the drivers of success. At Infineon, we believe this is only possible when high-performance components are delivering the highest levels of reliability. At almost every step in the digital and the analog world, we generate data that our devices collect and analyze. With a growing global population, faster digitalization, higher connectivity requirements, and huge amounts of collected data, the demand for reliable and sustainable data centers is greater than ever. Improving their overall energy efficiency not only reduces cost, but also has a positive impact on the environment. The role of data centers in our lives is evolving. Because of digitalization and the ongoing push for artificial intelligence, they will need to provide more services to more people. This will require a vast amount of information transfer, driven through both regional data centers and edge computing. To meet these demands, Infineon offers market-leading DC-DC converter solutions that support quick design-in options while providing superior efficiency, power density, and robustness. We offer flexible digital controllers with a superior transient response. Over 1 billion of our best-in-class power stages were sold into high-reliability, high-efficiency systems. They integrate Infineon's MOSFETs and can optimize total system solutions from DC to V-Core. Our smart and high-efficiency POL converters are designed for smart enterprise systems. We provide you innovation for best-in-class efficiency, telemetry, transients, design flexibility, and robustness. With our semiconductor solutions for data centers, we're also contributing to a greener and better planet. Part of your life, part of tomorrow. Infineon.
Second. Okay, yeah. Okay, yeah, so thank you, Dr. Van Long Pham, for the nice introduction, and really thank you for the VP community to introducing me and having me the chance to talking about my research work. So my talk today is basing on my paper presented at Apex this year in March in Orlando, Florida. The topic is about hybrid converters, adjustable four-level hybrid converters for single power tracking in 5G new radio networks. Okay, so a little bit about myself. So as an introduction for bio, so I'm receiving my bachelor degree at HUST in Hanoi, Vietnam. I'm working with EKIC groups with my professor Phạm Nguyễn Thanh Loan. So I obtained my master degree last year in UC San Diego in La Jolla, and I'm working for my PhD degree also in the same group, the iPower 333 groups with Professor Hạnh Phúc Lê. So my research direction involving the integrated power converters in silicon and gallium nitride recently, power amplifier architectures for 5G and 6G network, power delivery and management for data centers. And the talk is about today is my main research direction in 5G telecommunications. Okay, so these outlines for what we're talking today. So I'm talking about the 5G infrastructure, the power consumption in that. And the reasons why we need the efficiency, architecture for the power amplifiers. Then I'm talking about one technique to improving the power amplifiers, the PA efficiency, which is the envelope tracking. One approach to that is a discrete level tracking, and more specifically in my work, which is a simple power tracking. And I'm talking about what we're proposing for the converter is adjustable four-level hybrid converters, how we implemented it, and our measurement, and we come to the conclusion after that. Okay, so first of now is some of us are already experiencing the benefit of using the 5G network, and it can be seen as we can.
5G infrastructure.
I'm sorry.
30% more than efficiency per data than 4G. Net energy consumption for 5 times higher than 4G.
I'm sorry.
70% of energy by station and data center.
I'm sorry, is Julian talking? Oh, sorry. Yeah. So, sorry, I didn't guess that one. So I'll try to speak to my presentation, and I can answer the question later. Is that okay? Yeah. Okay. Yeah. So I'll continue with that one. So, but basing on that, considering the database or the benefit of the data transmission, it can be seen that 5G can offer 90% more efficiency management per data bit than compared to 4G because of the large data rates involving with thousands times faster than 4G. But the caveat is that like on the whole energy scale, like 5G infrastructure network can consume like 4 or 5 more like compared to 4G, which means that the actual like energy cost and the bill for the whole 5G infrastructure can be enormous and can placing a heavy cost on all of the telecommunication like industry. And a large portion of that, actually 70%, is on the infrastructure alone, which is involving the base station and the data centers processing the transmission and on the trafficking. And most importantly, that's coming from the base station. Because the characteristic of 5G on the frequency domain network, so it needing more cell, more base station to have the same coverage area as 4G. And each base station alone is consuming nearly like more than twice the power compared to the 4G base station. So that just means that like with a higher frequency, higher bandwidth that you can experience from the benefit of data transmission, you consume even more power. So we can say that like there's papers talking that like 5G is actually can be called like a energy vampire because sucking so many such powers. So we're able to have a sustainable in energy for the 5G and future generation of communication network. We have to make things those base station alone say more efficient. We have the infrastructure and less of a burden on the telecommunication industry. So we're talking about that like how to improving the efficiency and the power consumption of the 5G base station. So now let's see if like what part is in the power base station it actually consume more power. So basically it's like researching alone, you can see that the power amplifier part, which is using to amplify the powers from the base of the baseband and the IS front end, going next to the antenna, it consuming more than half of the power in the base station. So we're just talking about the 11 kilowatts per hours per base station, then more than half of the 6 kilowatts per hours just is used alone on the power amplifier. So to make it more efficient for the power amplifier is crucial if you want to make those base stations in particular and the 5G networks to be more energy sustainable. So let's take a look at what's challenging and what is the problem in the powers, amplifiers, efficiencies. So over here is that the chart outline some of the most common and very modern architecture for the PA networks and the efficiency that going at it. So so now the industry can now be very good with some of the most recent architectures like Doherty PAs, which can reaching the very high efficiency at very close to 80%. However, though the efficiency mostly is only obtainable at the peak possible powers, which is when you have the transmitted power is desired to be in saturated point. But in reality, in actual practical case, that is not always the case. Actually, it's like 90% of the time, the PA is working as very low power, which is called the average powers. So that's the event we call it the backoff. So with many generation of the mobile networks communications, the power backoff level is keep increasing. But our first GSM 2G networks, so we have all of those. The amplitude of the signal of the saturation is always at the saturated of the PA, so you have 0 dB for backoffs. Moving up to LTE is 4G, that number increasing to 8.5 dB. And now with 5G, the backoff level can be 12%, can be 12 dB, which means like the average power that the PA is working on most of the time is like 1/10 of the saturated power point that is inside. So what does it mean is that like if you try to use some traditional like Class B or Class KB EPA for the PA network in base station, you can easily wasting 90% of the power that you provided as heat. And so only 10% of that is using as transmitted power. So it's very common in an ad community for the continuous PA to have all these efficiencies of either 20%. And it can be less efficient. It can be big powers. So why is that the case? Because like how we providing one of the cases of why we providing input voltage. For the PA is that to avoid clipping at the peak application point, that even though your PA or the signal power is really low, but the PAPR or the peak to average voltage power ratio is very high. And the transition from the low power to high power can be very fast because of the high bandwidth of the characteristic of the transmission and the transmit of the signal that you broadcast. Does that mean that like you don't have this with fixed voltage supply, you have to providing a highest voltage level at saturation. But most of those power can be only spent on peak power, which is comprising in the time is only like 1 to 2% of the time. And most of that other time, like 90%, is always stay in the low power or low amplitude of the signal that you provided. That means most of the power that wasted is coming from that because of the voltage and the voltage amplitude of the signal that you broadcasted is less and less comparing to the peak voltage ratio and the peak voltage supply that you provided. So let's be clear, it says that the fixed voltage supply for the PA that you provided is going to waste a lot of power. So a way to approaching that is try to providing a dynamic voltage. So that is a topic I'm using in the PA to improving the PA efficiency. So that technique is what we call the envelope tracking technique. So instead of providing a fixed voltage supply for the PA, another additional circuit called an envelope modulators will dynamically changing or adjusting the voltage that go into the PA or the drain voltage to be following the envelope amplitude of the transmitting signals. So now what you need is like an envelope modulator that can synchronize with the envelope, then following and providing the voltage for the PA or the drain voltage, is following the envelope amplitudes. So what is the speed and the requirement for the envelope modulators? For currently the bandwidth of the transmitted signal is at like 100 megahertz. What does it mean? The envelope amplitude can be 4 times higher than that bandwidth that much. It means you can have to deal with like 400 megahertz with the 100 megahertz like baseband signals. So that's now the envelope modulator have to be able to operate at a very high bandwidth to be able to accommodate for the envelope amplitudes. So now we take a look at like what's the topologies and what do we do in the envelope modulator. So basically, you have to dynamically adjusting the voltage. Basically, this is the converters. You can use like a step down function, like in stepping from the high input voltage at the peak voltage to dynamically adjusting the lower voltage for the PA supply. So one way to doing that is using a linear regulators. So this is very common in older generation for GSM and LTEs, which is using just like an LDO side and adjusting the reference voltage with the envelope modulators that providing from the baseband like RF like interface. So the techniques we call it envelope tracking or envelope elimination and restorations. So the good thing is that we can using the high bandwidth comparing to the low GSM on LTE's network with like 20 megahertz. I would have to deal with 100 megahertz network amplitude of the bandwidth. But the caveat is a low efficiency, as you know. Another way to deal with and have the high efficiency is using switching converters. Examples over here using the buck converters. As you have like a very closely, you can following the exact envelope of the amplitude of the supply voltage. If we have like very high efficiency because of the switching nature of the buck converters, but it has the and we know this have limited bandwidth. You want to deal with the higher bandwidth of the signals of the transmitted signal, you have to either push for the higher switching frequency or utilizing other technique like multiple phase or multiple interleaving to achieving sufficient bandwidth to deal with the envelope bandwidth of the transmitted signal. Another technique to improve to leveraging both of the benefit of the two architectures in the hybrid structure, it combining both the switching converter and linear amplifier in the same envelope tracking modulator. So this is like a very common thing in the industry, both on the base station side and also on the handset side. We now can be sufficient like to go with the 100 megahertz bandwidth. However, as the bandwidth, maybe the wave, like generation of the 5G or even next generation, we're talking in 6Gs, that bandwidth just keep growing. Now we're talking about like 400 megahertz bandwidth maximum for 5G and potentially get the 1 gigahertz bandwidth for 6Gs. So that means that like you have to designing requirement for the envelope tracking modulators have to deal with now. It's like gigahertz range of bandwidth, and with keeping the same like topologies over here, that's sometimes can maybe not enough with the current like technologies. So many approaches need to be going in over here to try to improving the responsiveness and the bandwidth of the envelope tracking modulators. We're talking about like new device like gallium nitride, higher switching frequency allowable for the switching converters going into the envelope tracking. Waveform modulation, try to reducing the bandwidth of the actual envelopes like we're talking, or using the new PA architecture along with the envelope modulators, or having the new topology with the envelope modulators. So one approach into that, we're seeing it called the discrete level tracking. So instead of like continuously tracking the envelopes of the signal that you transmitted, we only like following this and providing only some of the discrete level with predetermined. So in LTE, it's called the average power tracking, which means the voltage that you're providing for the PAs is like discrete level, and it's only changing between the time slot. We call the subframe time of 1 millisecond. And the subframe time is when a certain amount of like traffic is going through. So over here is like now you have to providing the limited numbers of levels that can be easily done with the buck converters, and the only transition having to be provided within the time frame between the time between each time slot. We call it like cyclic prefix time or the transition time. It can be with average power tracking in LTE is like 5 microseconds. In current like handset devices in 5G right now, this also can be applying. And with like same time slot 5 microseconds. So the previous architecture of using hybrid converters can still be used. Another way of doing that we are talking about in the industry today is like using smaller time slot, which is the symbol time, which is the smallest data unit transmitted like in the traffic in the transmission link, which is talking about like total symbol time of like 4 microseconds, and the time between the each symbol is called the cyclic prefix time, which is the gap time like avoiding any clipping in the symbol and the data is transmitted, which is like maximum 290 nanoseconds. So now like the level of transitioning is only need to happening in and settling within the 300 nanosecond times. So now we try to design a converter that can providing multiple of the levels and can be able to achieving the transition in 100 nanosecond time frame. So approaching to that, like talking in academic, like in recent years, using a switched capacitor to manipulate that. The reason is like the switched capacitor is excelling in trying to generating fixable voltage levels, and be very efficient, and can be very fast to change, like because of like when using like an analog must, you can easily switching between multiple of those levels. So but the question is like how to be most efficient, that like you have to try to providing the level closest to the voltage amplitude of the envelope in delivery at the synchronous time. So that means you have the more efficiency, you have to increasing the number of levels you provided at the first place. So some of the like research work, we try to implementing a multiple of the analog must. So you can try to have like as many levels like providing from different converters. Some of the research have been providing in recent years, or try to using a switched capacitors like a ladder circuit example, like to generate 1 to 6 to 8 static levels, and then try to combining with the linear regulators and so the other previous technique, like to try to achieving the 5G like bandwidth of 100 megahertz. So the caveat is like you have multiple of those levels. It is for the switched capacitor to achieve the high frequency or high efficiencies. But like that increasing the number of complexity and the number of components you have provided in your circuit. So why the reason for that? Because the level generated by the switched capacitor is fixed level. So our approach into that, like if you can manipulate or try to generate those levels that can be tunable or adjustable in real time with the bandwidth or the bandwidth that we provided, that can decrease the number of levels that you have to provide. And that's what we are proposing over years. called adjustable four-level hybrid converters. So we have like a switched capacitor like structures that can generate four levels, and those four levels can be modulated or coming from a level modulators over here. And to achieving fast transient, we use a series of four analog modes, which are basically four checker switches that can switch between those levels to provide to the PAs. And those level can be switched between the symbol time, which we have seen earlier, the cyclic prefix time. Because the nature of the tracker and the analog modes, so transient can be sufficient within like nanosecond ranges. Okay, so let's talk about the operation of what we're proposing. So first, like the switched capacitor is basically a ladder circuit utilizing like 3 flying capacitor and 4 decoupling capacitor to achieving 4 level, generating from V in over here 50 volt down to V out zeros over here. So V out zero normally it's ground switched capacitor. Now we try to modulate in that ground. So the force level is a quarter from V in minus V out zeros. And this is in two phases with short between the two phases. Those 4 level will be generated into the 4 input of the tracker side that we're talking about in the next part. And try to modulating for the level modulator. So what we're using is almost the buck converter size below. So this is the 4 levels that we generated from the switched capacitor network. And when we say that we can using the tracker like to try to completing the transition within the cyclic prefix time of 290 nanoseconds. Okay. And for the level modulators that we're basically operating as a buck converter that's switching from the input of D1 that's sending from D0 to the duty cycle that can easily like controlling from the level inverters. The good thing is that the level modulator and the switched capacitor above it can be operated asynchronously. So that's the switching frequency of the switched capacitor and the level modulator can be like differently. So you can have like separately optimizing the two parts without compromising with the finals like efficiency and the actual bandwidth requirement for both. So you can apply the technique for the hybrid like structures and levels that we use above for the continuous envelope tracking for the level modulators over here to achieving levels that you needed. And can be optimizing process like in the run of the base station, basing on the data traffic like pattern that be present at the base station like on the time. So you can say that the tunability adjustable is on the go for the level modulators. Okay, so it actually like the post 4 level now can be adjustable from the duty cycle of the level modulators. And then it says that the tunability can offer like the tuner on the go of the V of zeros, or time at that time all of the 4 level of the switched capacitors. And after that with the fast combined with the fast transient of the tracker operations. Okay, so now it's like how to implementing and the implementation of all the components. So the interesting part over here is mostly on the output tracker side that we have. So because of the nature of the voltage, actual output voltage, it can be switching between those levels. So the VRs over here can be either higher or lower than the actual voltage provided. So some of the switches that for the tracker side need to be also have to be implemented with 4 quadrant switches. So over here, we're just using like a low voltage devices, like combining together, like to determine like the voltage driver level for the drivers that are attaching to the tracker size. So that is avoiding smooth operation without breaking like the voltage limits of the devices we're using for the 4 quadrant switches we're using. Okay. So what's this is our hardware implementation that we presented at APEX this year. Like on the boards are combining all 3 components for the proposed like 4 level adjustable with the switched capacitor networks, the level modulator, and the tracker size. And we tested with the actual like 50 volt inputs and the first with the DC operation. We're testing over here with the 50 volt inputs with one fixed level of the VF0 or the level modulator fixed of 10 volts. So this is stimulating a scenario where we have the specific like pattern of the data transmit networks. We can optimizing one of the 4 levels other predetermined like levels that can be suitable for the high efficiency of the specific like data patterning of the 5G base station. And with that, we can achieving like a peak efficiency of like 98.4% for the for the top output, which is also the voltage providers. At the generated level, we can achieve like more than 85% of the efficiencies, crossing the 1 amp output, which is corresponding to 50 watts output at the base station level, which is like corresponding to 1 cells of the base station that we could providing for macro base stations. Yes. So also testing that the PA was testing the output converter with one commercial PA and seeing the transition like responsiveness like, with the actual like RF inputs, like to seeing the interference with the actual transmitted signals. So this is one of our setup to use the converters with one of the commercial PAs available. Okay. So this the results of our transitions like between those levels. So the transitions between those 10 to 50 volts level. So the finals like from the lowest input of 10 volts like to the highest outputs of like 50 volts. We will be able to complete the only transition within the cyclic prefix time determined at 299 seconds. Can achieve even lower than that. So with this over here operating with a sub-gigahertz bandwidth of 780 megahertz, the input of like 50 volts. So we here is like one of the scheme that we're using for the transition with the step ladder. So we try to reducing all the ringing operations that can be that we introducing into the transition time of the transition of the force level. We also test this is actual like transmit it's like zooming out of the actual transition times. So as you can see that like the ringing only affecting inside the cyclic prefix time. So it will not affecting the finals like data transmission within the simple times. Okay. So we tested that with the actual like modulator signal over here is the lower bandwidth of the 5G network. We tried testing with the higher bandwidth. So we tested with the 50 megahertz bandwidth with the PAPR or the peak to average power ratio, also the level backoff, very close to the 5G standard nowadays, so very close to like 11 dBs. And actual efficiency when tested that with the commercial PA is that like in the levels around like 11 dB, which is the standards like 5G's power backoff level. The efficiency with the PA alone can be like from 20%, from 10% like to more than like 30% improvement, which is like close to like 3 times efficiency improvement with the commercial like class A PA, which are using now in the current base station network. So okay, so the conclusion to that is, so first off, it's like the traditional approaching like to how to improving the PA efficiency, which is the important part for the energy sustainable in 5G and its future like 6G communication mobiles. And approaching using discrete level tracking can be a good approach in tracking to the envelope tracking. So, and our switched-capacitor network like can be providing a lot of like configurabilities and tunabilities when using in actual scenarios. And we so one of our approaching right now is like researching into the control for the switched-capacitor and the level modulator to achieving the best efficiency possible with higher tracking speed. Okay. So that is the conclusion of my talks. Thank you everyone for listening.
Yeah, thank you very much for a very nice presentation. So can you keep the sharing the screen? So it's maybe good for other people.
Yep. Okay.
Yeah. So anyone have the question?
Could I have a question?
Oh yes,
sure.
Please, Dr. Da. Yes, please.
Okay. Good morning for everyone. Good morning, chair and the presenter. And very thank you for your nice presentation. So I have some small questions. So your topology is about hybrid converter. So you're using some RIC, mainly the capacitor. So as the voltage on the capacitor is balanced, could you tell me they are balanced or not? The voltage.
Yes.
Okay.
Yes. So let me over here the operation. Yes. So the flying capacitor is hard switching. So it's operating as a normal like switch capacitors. The hybrid part, which is only on the buck converter side, is only in extent is only regulating the ground of the switch capacitor, but the level that you generated from the switch capacitor itself is hard switching. So each decoupling capacitor over here will hold that voltage. It is exactly 1/4 of the voltage difference between V in and V out zeros. So reality is that even with switching between those levels, it is still maintaining the balancing, as we say.
Okay, so in practical, is they are natural balancing, or we need to control it? Do we need to control?
It is natural balancing because the switching. So the PA side on the decoupling side, the capacitance from the drain seen by the efficiency, seen by the PA is only 100 picofarads, and it is like very small comparing to the flying capacitor that we operating. Is like microfarad range. So the voltage drop even seen by the PA cell will not enough like to changing the voltage seen by the decoupling capacitors. Also because it's switch capacitor, the switching natures will ensuring the balancing operations.
Okay, thank you for your answer. And I have another question. Because some switches capacitor converter. So when switch is on and off, so how about the current to follow to the capacitor? Because as we know, sometimes when switch is on and off, so capacitor look like the voltage drop and it will connect. So I consider how about the current follow to the capacitor?
Yeah, so so it's not like in buck converters that you have like continuous current. So it is switch capacitor. So the current is actually the pulse current, and it have like very high peak current only at the beginning. That's when the capacitor transferring the charge. So for example, it's over here you see that in the first phase that like when CF2 actually charging the CO3 is over here. So the pulse current that flowing through even injecting very high current only at the beginning of the switch 6 over here. Yes, and yeah, so we call it like a hard switching limit. So the time that the capacitor actually transferring the charge is very small comparing to the duty cycle or the state that the circuit is bringing. So we're talking about the switching frequency of like primary kilohertz, but the actual like transition time or the transfer time is only nanoseconds. Like it depends on the like how close these two capacitors is facing it. So yes, so the switches, it experiencing large current, but it's only a pulse current in only very short time. So it doesn't have to sustain that large current for a very long time. And that's the nature of switch capacitors.
Okay, thank you. And could I have another question?
Yep. Yeah.
Okay, so in terms of the efficiency, so could you tell me how about the efficiency related to the duty ratio? When duty ratio is increase, so efficiency increase, right?
Yes. Okay. Yes. So I'm talking in two parts for the switch capacitor and the buck converter side. The buck converter, yes, it will depending on the duty cycle that you provided for the buck converters. However, the amount of current that the buck converter need to be provided. So over here is always the portion of the current that actually providing for the output, because the actual current that provided for the PA is coming from the capacitor side. And again, the capacitor is refreshing the charge by the capacitor, by the capacitors. So for the buck converter, yes, it will depending on the duty cycle, but that is not the significant part of the loss. The main part, which is coming from the switch capacitors. With switch capacitors, the loss and yes, the loss ratio is depending on the frequency that you're operating in. As I said earlier, the transferring task, the transferring time of the energy is only very short amount of time because of the hard switching characteristic. So if you try to operate it faster frequency, you spending less and less time needed for the circuit to stay in constant. Basically, like you, as I said, like you transfer the time only a portion of the duty cycle, and most of the time of that one is just staying constant. It doesn't do anything. So we try to operate it faster and faster. The charge that you transfer is quicker and should be potentially more efficient. But to sustain the high switching loss. So for switch capacitors, the loss characteristic and optimization is mostly depending on the switching frequency.
Okay.
And this, So like if you try to, so you try to operate with faster frequency, you only have to spend smaller capacitor, but you come back at the loss of like higher switching loss. So you have to get a better switches, or like try to do like integrated circuit with integrated switches. So that's one approach in our lab to doing switch capacitor integrated. So you can have like flying capacitor at nanofarads range.
Okay, thank you for your very clearly answer. Yeah, I have some question, but maybe I will contact to you later. I know Professor Luan, and so I will contact to you later because I see someone raise hand. Okay, thank you.
Yep. Yes, thank you.
Yeah, thank you very much for very good question and answer. So yeah, very interesting. And we have question from Dr. Hadi. So can you turn on the mic and if possible also video and make the question?
Oh, hi. Could you hear me?
Yeah, I can hear
you.
Okay, yeah, very interesting presentation. So yeah, my question is,
sorry, cannot hear you.
Sorry, Hadi, maybe we cannot hear you now.
oh, hello, can you hear me now?
Yes. Okay, now.
Yes, so
yeah.
Okay, so yeah, I just curious about how you operate the tracking circuit. So during the transition between the voltage level, so do you experience any dead band when there is no voltage output, or how you can precisely do the transition between one voltage to the other voltage so that it doesn't affect the output voltage, it doesn't affect the input voltage that is seen from the power amplifier. So yeah, I think you give some explanation, but could you elaborate more to give more detail?
So you mean like the how the level transition can be properly like without like breaking from the tracker side, you mean, or on the PA side?
Can be from the power amplifier side, so from the input side. So that I noticed that
Okay, so like from the PA side, like Alan mentioned that the transition is already happening in the cyclic prefix time. So so during the transitioning, you experience like a lot of ringing at the beginning. So the drain is always like switching like crazy. But like in reality, you can considering those ringing can be a part of the actual transmitted signal, and the PA itself will experience that during the transition. During the actual like symbol transition, as I mentioned, the drain itself, it had to experience carrier frequency like now 5G is like 2.4 gigahertz, and millimeter wave you can be like 24 gigahertz. So the actual like ringing itself is considered like a part of the envelope, but the envelope that part of the envelope is not being transmitted, so we consider noise. And the noise only happen when you don't have any traffic time, as you say. So on the device itself, it will not be affecting because it can consider part of the envelope. On the signal side, on the data side, it's also not relevant because it basically doesn't transmit signal at that time. So that is a part on the PA side. So on the tracker side, so the way that we implement is over here, that's fine. This is just our implementation on the 4 quadrant switches. And over here is like, this is a circuit that's trying to determine that the turn on and turn off voltage level for the gate drivers, which is using to turn on and turn off. So particular 4 quadrant switches for connecting each of the input or each of the level to the final PA outputs. So examples over here is that like I try to like I drawing over here is that like seeing one of the scenario when the output voltage of the PA is switching from the low level, which is like from BL2 is like, for example, like 20 volt. They're trying to switch that to like 50 volt. So during that time, like the the ground of the gate driver on the BSS part, it actually is staying at the lowest voltage between the two. So over here is that this is the second switches. It comparing between the actual output at the time and the VL3, which is the input side, and we could choose the lowest one. And I have like isolated power supply, which is providing the VDD for the gate driver, which is only 5 volt compared to the VSS. So you only need to decide what is VSS for each of these switches and the gate drivers, and the driver will follow that, because I have like a separate like voltage supply for that. So yes. So depending on the output voltage, and the actual is like one drain and the other drain of the 8 switches. So like basically they do 2 back-to-back diode, which is also can be the body diode. We determine what is the lowest voltage between the two, which is also the source voltage, and designing that for the gate driver, and you're ensuring there's no breakdown between the two. Okay, so I hope my answer is clear enough for what you want.
Okay, yeah. So by using this 4-quadrant switch, so even though I guess maybe there is a time during this transition, so all gate signal for the tracker circuit is off. So by using this configuration, it's still there will be no breaking of voltage until it wait for the other. Let's say when you turn off the switch for the 24. Then after that, you transition to switch for the 44. So between that, is there any, let's say, dead time?
Yes. So okay. So between that time, between the all 4 of those level when all those 4 switches will turn it off, actually the output will stay in at VL1, because like basically it's a reverse diode connection will leak into VL1. So what does this mean is that like actually all of those switches source over here, all those switches will stay at VL1. So it is lowest voltage between all. So you don't have run into issues that like those sources actually higher than the drain, and you can flip. So even in that time, it means no scenarios that you can break down. The only like condition that you have to ensuring that the source over here, the source of all the switches have to be dropped first on. It have to be the body diode need to be like quick enough to correctly biasing all of the source of the back-to-back switch of the 4-quadrant switches to be as the lowest between the 2 terminals over here. And that's actually what I implemented in one of the chip version. Actually, what I do in that time is like I try to switch the source of the 4-quadrant switches to the lowest voltage possible. And when you try to switch the voltage, it's a drain voltage. So you can switch to any higher voltage than you want in the source.
Okay, so during the dead time, the voltage will not drop to 0. It will maintain
it will drop to the VL1, which is the lowest voltage in all 4 of the voltage. So the lowest voltage possible for VL, even in that time, is VL1 minus 1 voltage drop. To be exact.
Okay. I think I got the idea. Yeah. Thank you.
Yeah, thank you very much for a very good discussion. Yeah, I think there are still many questions, but we have a question from chat. So Justin Nguyen, can you turn on your mic and video and make the question? Yeah, please, if it's possible, please introduce yourself. Yeah, thank you, Hadi, for a very good question. Yeah. Hello, Justin Nguyen, can you hear me? So yeah, he just like he have a question about the control loop. So yeah, maybe later he can make the detailed question.
Hello? Yeah, can you hear me?
I can hear you.
Okay, great. Okay, thank you for a pretty good presentation. Okay, my name is Jason Nguyen. Okay, and I have a couple of questions. So because of the output voltage switch to different levels, so how do you regulate the feedback control loop for different voltage? That's my first question. And so with different output voltage, your bandwidth feedback control loop will be changing. How does that impact your conductor susceptibility? and that would affect your power amplifier performance.
Yeah, sure. So actually, like the controlling side of the level is like actually the next part of my research on doing that. So I'm giving some like brief details. So currently now, what I setting the converter is working at is that actually the V0 can be one fixed level, the tune level. So that level can be tunable like one half during operation. So that can be predetermined, pre-optimized based on the data pattern. So we have like the data on the 5G like traffic networks that like it can running a very long time, like in days or even months. So it even determines like what is the ball level is actually the most efficient that we try to provide. So instead of like for conventional like ball level, which is only like 12.5 volt, like 25 volts, 37 volt, and 50 volt. But now you can tune it like, for example, over here, what I can do, it actually is here like a 50 volt, 40, 20, and 10. So now the numbers, the set that we provide in the level is a limited, but it's more efficient comparing to a traditional switch capacitors. That's the first thing I say. Our next part on the research actually, and we're saying over here, try to do it like on the go, which is like actually the V0 is changing. It's changing with the actual like bandwidth or actual data rate that it sees. And first off, the rate of changing, and you say is not much. You see is over here that like I try to do is like with actually on the go with the microsecond range. But actually, the most of the transitioning is a simple time. You can say it's only 4 microseconds, which means the level transition within the on 4 level is like 200 kilohertz, and the V0 changing is even lower than that. We're talking about even days or even hours cycle. So the bandwidth of the level modulator doesn't have to be that fast. It can be only like 10 kilohertz or 100 kilohertz range. It can be easily like implemented. And yes, the bandwidth when we change like that one will affecting the carrier or the PA performance. But as I say, it's like it's when we determine the actual transition of the level modulators. As I said earlier, that like we have like a different like time slot like configuration for the PAs like architectures. Over here are switching on the level of the smallest unit, but the level that you try to switching for the level modulator can be happen a subframe time, which is 1 millisecond. And I said, in that 1 millisecond, the actual data that you transmitted is not important because it's not the actual data. It's only the toning signal or the preambles like synchronization time slot. So the actual like data is not just is not being affected overall in the whole system. So that's what we try to one approaching in our research is that we only try to switching the level of the metal very rarely, like every hour or so. And it is happen at between the subframe time. It's usually like 1 millisecond time frame. So yes, like it will not like on overall will not affecting much to the actual data rate of the signals. But yes, we are trying to look into like if we can actually switching the level modulator level, the VR0 within the data transmission time, and what is the impact on that one? And that's actually like our part of what I'm working right now.
Great. Okay. Great. Good. Thank you.
Yeah, thank you. Thank you for the questions.
Yeah, thank you very much for a very nice question and answer. So, is anyone have question? Yeah, actually, time is over, but if you still have the question, so we can still keep time for 1-2 questions more. Yeah.
Just a quick question from me. You show the efficiency graph, which is, I'm not sure if it's very high, but I guess it's acceptable. I wonder, how do you compare it with other topologies in the same class? Is it better or similar?
Oh yes, so yeah, so the one thing is that like Actually, that this kind of like architecture is firstly implemented for the handset, which is like very low like voltages. The handset like I refer in the paper is they're working at like 5 volt level. So yeah, so this over here I'm comparing like all these on the switch capacitor if like side by side like imagine. Yeah, so like over here is like I'm using over here with the comparison with the actual like PA like actual like continuous PAs, but like reminders that like over here is that we can providing like multiple level at the same time with the efficiency like comparing to the switch capacitors, and also it's like as I said the efficiency of the switch capacitors like improving like or depending on the frequencies you operated, which is coming from the controlling side. So over here is that like I'm not being like very optimizing over the switching frequency that you provided, but it can be a bit more efficient with the average drawing over here on the measurement band results. Yeah, so that's my side.
Just a curiosity, because if I just replace the switch structure with something different but providing similar functionalities, for example, if I add BAD with 4-level outputs and then switch the outputs, would it be more efficient?
Oh yeah, so you mean like replacing a switch capacitor level structure with something that can providing 4 levels? That you mean?
Yeah, for example, dual active bridge with different winding with different voltage ratio.
Okay. Yeah. Yes. So first up, like we basically like you providing like four different converters. Yeah, 4 different converters like to trying 4 levels. So so that's what I try providing. So you try to doing with like 4 different converters, but basically you start off first. You have to deal with like 4 active bridge with like full device range of the like for example like 50 volt device. So you have to deal with like high voltage device first in order to generate that 4 voltage. And you're talking about like 4 different converters to try to synchronize it to one. So that one's approaching in the previous like one approach in the previous like architectures that is mentioned like above for the multi-level switch capacitor. Our architecture over here doesn't require high voltage device. Although each switches are low voltage device. It's over here, each switches only have to block maximum 1/4 of the input voltage. So that's the beauty of it, that you can use like all low voltage devices in this converter alone to realizing like the voltage generations.
No, I don't think so. For example, if you want to connect, for example, the switch SW4.
Yep.
I think it's
that
no, the number 4. For
this one?
Yeah. For example, that one, I think it had to endure the maximum voltage. 40
Yes. Yeah, but in the tracker side, but the tracker is on the tracker side. But like even if you try to replacing that with the 4 DC voltage, you still have to deal with the same tracker side. Yeah. But on the level generation alone, on the switch, actually the converter side, you don't have to use like high voltage device. Yes.
Yeah. Sure.
So that's one of our like oriented our direction on this one actually, because it's only have to use like low voltage devices on the level generation, like all the switch, all the actual like DC converters. So it can be very, very enticing to use that in integrated versions, because even negating any affecting with the PA with the lower parasitic patterns, and we can leveraging like the integration of the chip side.
Yeah, I'm not in this field, but for 50 volt, and you want to use low voltage, it is a bit weird. For my field, if you talk about a few kV, and then you could say it's a lower voltage device that will be attractive. But for this application, it's a bit difficult for me to find benefits. But well, it's not my field, but it's interesting. Thank you.
Yes. So we want to talk about that. Like I'm happy like to finding further info with you. So that's one of the direction in our lab to trying to doing like high voltage like application with low voltage devices. Yeah. So that's why we try to like populate the idea with the community. So thank you for the attention.
No way. Thank you. Okay, I think it's about time to finish the sessions for today.